Hello, in this lesson, can we talk about the binomial distribution? So the binomial distribution just describes the number of successes in a fixed number of independent trials. Independent meaning each trial doesn't affect the other. So each of these trials has only two outcomes. It can either be a success or a failure. So let me show you what I mean from our previous lesson. So let's say I toss this coin once, and I would count it as a success if it shows me a head. Otherwise, if it shows me a tail, I would count it as a failure. So if I toss it like this, you see I got a head. So that's a success. Otherwise, if I got a tail, then that would be a failure. So that's what we mean when we say each of the trials has only two outcomes, a success or a failure. Then the probability of success, for example, in our case, the probability of getting a head is given by P. Then the probability of failure, which now in our case is the probability of not getting a head, is given by Q, where this Q is 1 minus this probability of success. And actually this makes sense because from the previous lesson we said that probability operates from 0 to 1 or from 0% to 100%. So in this case, if my probability of success was P, then to get the probability of that thing which did not happen or the probability of failure, then I need to take 1 and subtract the probability of what happened, which is the success. Or rather, in simple terms, I need to take this 100% and subtract the probability of success. So in our case, let's say for example, if we already know a fair coin can give us a sample space of either a head or a tail, and both of these two have an equal chance of appearing. So the probability of each of these appearing is half. Then it means if I got a head, then the probability of success, which is given by P, is then a half. So from this, now that I know the probability of success, I can also know the probability of failure, which is given by Q, which is equals to 1 minus the probability of success, but I already know the probability of success is half, which now becomes 1 minus half, which is also half. So the probability of failure is also half. So that's the logic of that statement. So the binomial distribution formula is given by P is equals to X, which is equals to K into N choose K, e raised to power K, Q, N minus K. So if I write it here, which we have P, X is equals to K into N choose K into P raised to power K into Q and minus K. What I mean here is this is just the probability of choosing K items from X items, where now in this one, N choose K is given by this formula. N choose K is given by N factorial over K factorial into N minus K, but now factorial. After this formula in lesson 5, if you don't understand what it means, you can review lesson 5, then come back here. Then here, P represents the probability of success, and then Q represents the probability of failure. Then N is the total number of events from where we are choosing or many ways we are going to choose k trials or k items from n, and then the k itself is the number of trials we want to perform until we get the first success. So in this case, if we try an example here, somebody tells you to toss a coin 3 times, then find the probability of getting exactly 2 heads. So first of all, we are tossing a coin 3 times. So our hen then will be 3. Our hen will be 3. Then we want to know probability of getting exactly 2 heads. So we will say the probability, now here our x becomes 2 is equals to n, choose k, into p, which is the probability of success, raised to power k, q, n minus k. And now look, we already have n, we have k. And we said to get, first of all, to get this nk, we apply this formula, which is the coefficient expansion formula. You can review it on lesson 5. So to do so, I need to put 3 here, then k, which is 2, like this. Then is equals to n, which is 3 factorial, all over k factorial, but now we know k is 2, into 3 minus 2 factorial, which now becomes 3 factorial divided by 2 factorial, into 3 minus 2 is 1, so 1 factorial. So it becomes 3 by 2. I'm just expanding this factorial, but because I have a 2 factorial here, I don't need to go further. For that, I can just put it 2 factorial there. Then I also put 2 factorial here. 1 factorial is just 1. And 1 multiplied by any number is just 1. So we can stop it there. Then I cancel that 2 factorial with that. And I remain with 3. So this part here, it will be 3. And then the probability of success, and again the probability of failure, we need to get them so that we can also put them here and expand this part. But you see, since we are tossing a fair coin, then it means either getting a head or a tail, they have the same probability, or they have an equal chance of appearing. So the probability of getting a head, which I could call a success, then to be half, and also the probability of getting the probability of not getting a head, which now is the failure, would be q is equals to 1 minus half, which will be a half 2. So now I come here and replace them. We already sorted out this part, we know it's 3, so we can add on for now. So, but now I know the probability of success is half, then raised to power k, but we already know k is 2. Then q, you already know q is half again. And now n, which is n was 3, but 3 now minus 2. Because k is 2. So it becomes a half squared is the same as a quarter, because I squared this 1 and also this 2, then multiplied by 3 minus 2 is 1. So half raised to power 1 is just a half. So I multiply by half here, which now becomes 1 by 1, which is 1, then 4 by 2, which is 8. So the probability of getting exactly 2 heads when I toss a coin 3 times is 1 over 8. So can we try another example? You are told a factory produces bulbs. The probability of a bulb being defective is 0.1. Then somebody tells you to find the probability that exactly 2 out of 5 bulbs are defective. So in this case, the total number of bulbs produced are 5. So in our case now, n becomes 5. Then the probability of getting a bulb being defective is 0.1. So that p is 0.1. And then from here, we need first of all to calculate the probability of getting a bulb being not defective, which is given by Q S1 minus the probability of success. But we already know the probability of success is 0.1. So Q now will be 1 minus 0.1, which now becomes 0.9, like that. Then you are told to find the probability that 2 out of the 5 bulbs are defective. So in our case, then K becomes 2. So we have K is equals to 2. So now we have all the values. So I can start with saying P, which is given by X is equals to 2, is equals to N, which is K, then into probability of success raised to power K into Q minus N minus K. So in this case, we can start with N choose K, and we apply our normal formula where we said N choose K is given by N factorial into K factorial into N minus K by now factorial, which is the same as N. We already know N is 5, so 5 factorial into K factorial, but we know K is 2 factorial into N, which is 5, minus 2 and our factorial. So this becomes 5 factorial into 2 factorial. 5 minus 2 is 3, so 3 factorial. So which becomes 5 by 4 by 3 factorial. Because I have a 3 factorial here, I want to divide it with this 3. So I say 2 factorial like this, then again 3 factorial like that. So this goes with this, and then I say 5 by 4, however, 2 factorial is just 2 by 1, which is 2. So this 2 goes with this and remains 2. So 5 by 2 is 10. So this part here is sorted. We know it's 10. Then we do have this part here, where we have P raised to power K, then Q N minus K. But we already have the probability of success being 0.1. So we just replace it here with 0.1 like this, raised to power K, but K we already know K is 2. Then we already know Q because we got it here as 0.9, but now raised to power N minus K, but we already know N is 5, so 5 minus K, which is 2, which now becomes 0.1 squared, then again 0.9 raised to power 3, like that. But don't forget, we also have a 10 somewhere here. So after we do all that calculation, we need to multiply by 10. So can we try in the calculator and see what this 0.1 will give us and this 0.9 cubed will give us. 0.1 squared is just the same as 0.1 multiplied by 0.1 again, which is 0.01. So here this part we have which is equals to 10 into 0.01. Then again, we go back to 0.9 cubed. And 0.9 cubed is the same as just 0.9 multiplied by 0.9 again, then multiplied again by 0.9, so that now it becomes 3 times. So it becomes 0.729. So when I come back here, then I say it's 0.729. And then I can again multiply this 0.729 with 0.01. In the calculator, you can just use the calculator, multiply this with 0.01. It now becomes 0.00729. 0.00729. 0.00729. But you remember we had a 10 somewhere, so I multiply again by 10, which now moves 1 0 here and becomes here. And the answer becomes 0.0729. So the probability of having 2 out of the 5 verbs being defective is 0.0729. Can you try this question here? This one. See if you understand the logic of the binomial distribution. Bye for now. Let's meet in the next lesson.